this video, we're going to talk about nuclear decay equations. And so I have some examples of each kind, and we're going to go through how to do all of those. But I wanted to start with making sure you know the symbols for nuclear decay. So first of all, there's one symbol that looks like this. It's 42He. This is known as the alpha particle. An alpha particle is, as you can see, the same thing as a helium nucleus. So that's why it has the symbol for helium. This shows that it has a mass number of 4 and contains 2 protons. And so this symbol here, anytime you see that, that means it's an alpha particle. A beta particle looks like this. And a beta particle is, it's basically the same thing as an electron. That's why we use the little lowercase symbol e to represent this beta emission. And there's one others, which is gamma radiation, which looks like this symbol. This is gamma. Now, each of these types of particles here, well, actually alpha and beta are particles. Gamma is not a particle, it's just energy. So if you remember the electromagnetic spectrum, we see that this is just energy. So we have here that these are particles, and this here is just energy. And so these are all types of radiation that can be given off, going from the least harmful to semi-harmful to the most harmful type of radiation. So if you're exposed to alpha particles, it's actually okay. I don't know if you knew this, probably didn't, but if you do research on this for your project coming up soon, you're going to see that alpha particles are actually found in smoke detectors, which you have those wherever you live because it's required by law that you have them. So everyone comes in contact with alpha particles on a daily basis. Gamma radiation, on the other hand, not so much, but if you do come in contact with gamma radiation, that's the kind that's likely to cause deformities and cancers and things like that. So, okay, that's just a aside for you here, but let's look at our equations now. So starting up at the top, we have lead, which is atomic number 82, so it has 82 protons, and it has a mass number of 207. And what this is saying is it's going to emit an alpha particle, and we want to find out what's left over when it emits this alpha particle. Well, to do that, what we know is the sum of the mass numbers, which are the top numbers, must be equal on either sides of this arrow. So whatever we have adding up over here has to equal 207. Well, if this is 4, that means 4 plus something has to equal 207, and wouldn't that be 203? Because 203 plus 4 equals 207. Same thing applies for the bottom number, which is the atomic number. If we have 2 down here and we need 82, that means that we have to have 80 as our atomic number. And then the next step is to look at the periodic table, find element number 80, which is mercury, and put in its symbol. So this is an example of alpha radiation. The next one here, we have the same thing. We're looking at lead with a mass of 207 again. This time it's going to go through beta emission. Same rules apply that we're applying up here. The mass numbers at the top must be equal on either side of the arrow, which means this has to be 207 because the 0 is there for the beta emission. And on the bottom, it has to add up to 82. Well, if we have -1, what plus -1 equals 82? Well, wouldn't that be 83? Because 83 plus -1 gives you 82. And then again, we look at the periodic table, find the element symbol for number 83, and that is bismuth. Now, this one here looks really similar because we have this beta particle again, but this one's a little bit different because see how it's the opposite process? This one is releasing this particle, so it's beta emission. This one's called electron capture, but it works the same way. Our numbers at the top need to equal up, so 14 has to be our number at the top over here. The numbers at the bottom have to add together as well to be equal, so we need 6, so -1 plus 7 would give us 6. And element number 7 is nitrogen. And then finally, at the bottom, we have our example of the gamma radiation. So this lead is going to give off a gamma particle or gamma radiation, and our numbers need to add up in the top, so this has to be 207. Our numbers at the bottom have to add up, so this has to be 82, which leaves us with just lead again. And so see how here, even though something was emitted, it didn't change anything about the The element, that's one of the key things about gamma radiation, is that it doesn't change it, but rather it just emits a type of energy. And remember that energy is not matter, so therefore this does not change.